Analysis of variance can be used to test for marker trait linkages using linear models. In this video, Dr. Francis describes the concept of the linear models, especially related to the components of the expected mean squares and f-test. The ANOVA output interpretation is discussed. Additionally, he also talks about a function in R to estimate the effect of allele substitution and the variance.
We're going to talk about our marker trait models. So the Edward Stuber and Wendell 1987 paper lays out a theoretical basis for using regression to test for marker trait associations. And the basic marker model is of the form y is equal to mx plus b, right? It's a linear regression model. In this equation 1, I'm writing out y, which is my phenotypic vector, is equal to the mean of the population plus a main effect for marker plus the genotype within marker variance. And this genotype within marker variance turns out to be the error variance. Occasionally, well, this model here would be written out in R in this form. LM is equal to trait by marker. Okay, we don't have to specify the error. That's done by default. It's the same as SAS would do it. This is a basic marker trait model. In some cases, you might have a block effect. Okay, so if we didn't reduce our data to a block, to a best linear unbiased predictor, we could have environmental effects in that model. Right. The only reason I'm bringing this up is because if you ran this linear model as an ANOVA, your effects are going to be tested with the error term by default. Our f-test should be the mean squares for marker divided by the mean squares for marker within genotype. So in our first model, in model 1, that's actually our error. But in the second model, our error is not the same. So if we want to do the proper f-test, we're going to have to do it manually. So that if you have more terms in the model, you have to think very carefully about what the proper f-test is for the term that you want to test. So that's a bit of an aside. Let's concentrate on this simple model. This is our residuals. This is our marker effect. This is our phenotypic value. So when I run it, this is what I get. Okay, so how do I interpret this ANOVA? So the interpretation then is that this marker, which has this ungodly name, SolCap-SNP SL10246, is linked to a gene or genes that control fruit number. So there is a significant, another way of phrasing it is there is a significant association between SolCap-SNP SL10246 and the trait fruit number. Let's go deeper into the interpretation of this. Okay, so for model 1, the R squared value can be interpreted as a measurement of the proportion of phenotypic variation explained by the QTL. So have you guys ever heard of this as like that QTL explains X% of the variation? Right? That's directly coming from this R squared value. Okay? Now for model 2, the variance associated with the marker can be expressed relative to the total phenotypic variance. Okay, and so let's go back and look here. Okay, I've kind of written two markers, one that has like a block effect or some kind of environmental effect, and one that doesn't. This model is simple. If I get an R squared value from this, that R squared value is interpreted as the proportion of variance explained by the linkage of that marker to a gene. Again, we looked at using LME4 to extract variance components. So in this case, I can express the variance associated with marker as a proportion of the total variance, and that's going to be analogous to the R squared in model number 1. I can't use the R squared in the second model because that R squared value is for the whole model, not just for the marker effect. So again, going back to this ability to extract variance components, if I have a more complicated model, I can still extract variance for the marker effect and express it as a proportion of the total variance. So coming back here, Let's look at the mean squares. Okay, so these are the expected mean squares for the model. They've been adjusted to reflect the genetic consequences or the genetic properties of that f-test. So B would be the number of replicates. C is a recombination fraction that separates the marker from the QTL. N is a coefficient that's related to population size. Okay. And then G is the genetic effect. Sigma squared GQTL is the part of the error variance that cannot be explained by the QTL. So here's the implications. If we do the f-test, we isolate this term. That's what the f-test is for a marker trait association. So the f-test is related to the population size, the recombination distance of the marker from the trait, and the genetic effect, the strength of the genetic effect. Now, as an experimentalist, what can I control in this equation? What do I have control over? Population size, right? I could have some control over recombination. How would I control recombination? Remember, it's the distance of the marker from the trait. So my population size, the structure of my population. And if you increase your marker density, you're also going to, by chance, you're going to get markers that are closer to the QTL. But so more markers, more recombination, larger populations. So if C, okay, how do we express recombination? Okay, and if we don't express it as centimorgans, if we express it as a recombination fraction, what does 0.5 mean in recombination? Unlinked, no linkage, right? So what happens if I plug 0.5 into this equation? It's 0. What does an f-test of 0 mean? It's not significant. Thinking about this equation, this equation relates directly back. It relates directly back to the expected mean squares of our f-test. Okay, and it points out to us that the importance of increasing population sizes and possibly increasing marker density. Okay, so the power of mapping is related to both marker density and population size. Okay, here's the important thing to keep in mind, is that as we increase marker density, our ability to distinguish one marker from another based on recombination is wholly dependent on population size. So increasing marker density in a small population doesn't really help. Increasing marker density only helps if you also increase population size. So in the context of mapping, especially when we're doing this single marker trait analysis, the most important thing to think about is big populations. So again, just to reiterate, the interpretation is that there's no difference between the marker classes. If the null hypothesis cannot be rejected, it's either because there is no linkage or there is no genetic effect. The R² value can be interpreted as a measurement of the proportion of phenotypic variation explained by the QTL. And so everything that I've just talked about is in that Edwards, Wendell, and Stuber paper. So you guys now have the set of tools to replicate that work. So moving back to R, we can use the summary command on the object fit1, and that's going to give us two really important things. One is it's going to give us our R² value. The other is it's going to give us estimates associated with each of the alleles or allele states. So what is our intercept in this case? I mentioned this when I showed you this summary statement. These estimates can be used to estimate the effect of allele substitution and therefore give us information on gene action as well. What's the proportion of variance explained by the linkage of this marker to a gene or genes affecting fruit number? Yeah, it's 5%, right? So I tend to use the adjusted R², so it's adjusted for population size. It's going to be more conservative, right? You could say 7% if you wanted to inflate it, but really I think this is better. About 5% of the variation is explained by this marker QTL linkage. Now let's take a look at these estimates. So this is how we can look at it. We have our A effect, 1.1342, B negative 1.5536. The mid-parent, if you just average those, would come out to be a negative 0.20965, and H is falling right here. So if we use the allele substitution, which assumes additivity, the effect on allele substitution is going to be 1.34 fruit. But the gene action is in fact partially dominant, so this isn't falling right on that mid-parent line. So from the analysis that we've just done, from the marker trait analysis that we've just done, we can conclude that there is a locus linked to SOL-CAP SNP SL10246 that is significantly associated at a p-value of 0.019. It has an effect of increasing the number of fruit by up to 2.6 per plant, the difference between homozygous B and homozygous A, and it explains 5% of the observed variation. We've just taken something that's this like diffuse quantitative trait. We get this normal distribution, it's really difficult, and we can say next to this marker someplace is a gene or genes that acts in a semi-dominant form. It can increase the number of fruit by 2 to 3 per plant, and it explains 5% of the variation. We just Mendelized a QTL. If we know the position of this marker, we know the position of this QTL. We know its action, right? We know how it behaves when it's homozygous for one allele, heterozygous or homozygous for another. Can you show that you can take lines out of this population that have the AA genotype and cross them to other things that have the BB genotype and replicate this effect in subsequent generations? Can you use this to move populations forward? So rather than just replicating it in a different environment, replicate it in a different cross. It's what we would call a validation population. So this is our hypothesis forming generation. Let's take it to another generation. Let's make more crosses and show that we can actually use this to predict.